Greetings, everyone, and welcome to the Complexity Lounge, a meetup where we gather to talk about all things related to complexity and complex adaptive systems. I'm Jocko Selberg, and somewhere out there drinking her hot toddies is the multifaceted, uber-talented Barbara Frontera. Together, we co-host the Lounge. Before we kick it off, just a few ground rules. We will be recording today's session, so if you do not wish to be recorded, please make sure your camera and microphone are turned off. We also ask that you keep the side chat activity to a minimum during the presentation. After Barry's talk, we'll have a question and answer period and hopefully a nice conversation with you all. You can raise your hand or just send your questions directly to Barbara with a big Q in front via the chat so that she knows that it's a questions. But please hold off on your questions until after the presentation, as the presentation is sort of structured that way. So hold off on your questions. The recording will be posted on Vimeo on our Complexity Lounge page in the next couple of days, and that is where you'll find all of the past videos from the lounge. Our guest today is Barry O'Reilly, and Barry is the founder of Black Tulip Technologies and Ph.D. researcher within the field of complexity science and software design. His work focuses on finding ways for software architects to make decisions in increasingly complex environments, which is right up our alley. He is a former chief solutions architect at Microsoft Consulting and was the global lead for Microsoft's solution architect community. Today, Barry will be talking about residuality theory. Residuality reveals a new way of looking at complexity, software, and traditional methods of modeling, and raises questions about the invisible, accidental, philosophical worldview of software engineering. This talk will look at residuality both from a practical and philosophical perspective to provide a new worldview and set of tools for complexity practitioners. So Barry, welcome to the Complexity Lounge.
Hey, thank you, Yoko. And I think there's a mute all button we can use to calm things down a bit there on the participants. So let's get started. So we're going to talk today about residuality theory and the philosophy and the practice of it. And it's a new theory that has been created within the software industry, within the confines of software architecture. And I'm going to start off by talking about the philosophical side of things and the philosophical implications of what I'm saying as much as I can, and then look a little bit more at the techniques and the ideas that have been created as a part of this. So as Yoko already said, this is me, and today's talk is going to be based on mostly around this paper on residuality theory, random simulation, and attractor networks, which was published last year, and also some snippets from a paper that's about to be released on residuality and representation. This paper here is a little bit more technical. And the paper that's coming is a little bit more philosophical in nature. So they're two different sides of the same coin. So we'll start off by talking about the problem. What problem is it that we're actually trying to solve? And the problem is, why is software architecture so difficult? So software architecture is the practice of making decisions about the structure of software applications. Why is it so hard to do that? Why do we struggle with it? And why do we get it so dreadfully wrong so often? And there are lots of opinions on this, of course, but it can be boiled down to one particular problem that we, as an industry, have found incredibly difficult to solve over the last 50 or 60 years. And I call this the problem with X. And essentially what we have to do when we build software is that we have to build this little box, and we have to make a structure about a structure in this little box. Which components are there? How many components should they be? What platform should they run on? How should they be related to each other? How should they talk to each other? How should they know about each other? That's what software is. And this is an ordered structure. And this structure is ordered. And if you live in the Kinevan world, then you would say complicated. It's a complicated structure. There's a lot of people in the software industry who will tell you that software is complex, but it absolutely is not. Software is a machine. It does exactly what we tell it to do. It doesn't do anything else. It's a set of compiled instructions. And what we do with this innocent little software structure is we place it into an environment, and that environment is absolutely not complicated. It's a very complex environment that has people in it, and it has markets in it, and has organizational structures, and it has societies, governments, and all of these things all moving all the time. And what we have to do is we have to decide on the structure and then place the structure into this environment. And as soon as we do that, we get this X that pops up in the environment, and we don't know what that X is beforehand. X can be anything. It can be a change in the law. It can be fluctuations in the market. It can be changes in consumer behavior. It can be changes in competitor behavior. It's an incredibly wide range of things that can happen in this bubble that's going to surround our application. And there are lots and lots of these X's. And when they pop up, they impact the structural decisions that we've made in our software. And very often, they will show us that the structural decisions we've made in our software weren't prepared for what was going to happen in the environment. And we have to then tear our architecture apart, go back to the drawing board. We have to rebuild. And that's something that's incredibly expensive. And the way that architecture has traditionally dealt with this overwhelming problem, because all of the things going on in here, one of the first instincts we have is to try and write down all the X's, list all the X's, predict all the X's. And that turns out to not be a particularly good approach. And because it's absolutely massive and it's subjective, and it's very, very difficult to do. So what we do is we simply decrease the size of the environment. We make it smaller, and we do that with a bunch of tools like requirements engineering and risk management. And so we start to make this bubble much smaller by saying, this is never going to happen. We're never going to need this. There's a very low probability that this is going to happen, and there's absolutely no scientific foundation for any of these statements. We're just making things smaller so that life is easier. And the same with requirements engineering. Say, well, we're going to make you speak in a particular way. We're going to make you be precise. We're going to make you talk about what's happening in your environment, and you're going to have to say things that are smart. And if they're not smart, then we're going to ignore them. We're going to sweep them all under the rug. And what that does is it shrinks this thing. It makes it much easier to work with. It makes it seem like there's some form of certainty in what we're doing, and then we can build our architecture. But it doesn't escape the reality of the wider system. Eventually, it does promote action, though. It does get us to build something. It stops us from freezing. And analysis paralysis is a well-known, very famous problem within architecture circles. Eventually, though, this red X is going to pop up, no matter how much we fool ourselves that we have control over this environment. And that red X is going to have exactly the same effect as the other X's I described. It's going to test our architecture. It's going to test our hypothesis. And very, very often, given the size and scope of these environments, it's going to prove to us that we're wrong. And we're going to have to rip that architecture apart. We're going to have to start all over again. We're going to patch things. We're going to be encouraged as time moves on through a project or an initiative. We're going to be encouraged to make quick fixes. And the perception of the people who pay for these kind of software systems, their perception of the quality of this system is how well does it survive these unknowable X's? Because even though they're unknowable, it's still a problem. And if this was an unsolvable problem, then we would have to just give up and say that the only way to do this is just to build something, put it into the environment, wait for it to break, rebuild it, and just deal with it like that. And that's sometimes called agile. And that would be the only way to solve the problem if there didn't exist a whole bunch of architects who consistently build architectures that survive in these kinds of conditions. And so this entire talk, my entire project, is about studying those architects and the techniques they use to be able to deliver systems that seemingly do the impossible, that survive things that the architects themselves didn't know about through their structure. And so several years ago, 9 years ago, in fact, I went over to head office in Seattle and spoke to some people there, and they said, look, we want you to start a new project. We want you to instead of doing architecture, which you've been doing for a while and you've been doing very well, we want you to create the next generation of architects. And I said to them, well, what do you mean? What do you want me to do? What do you want these people to be able to do? And they said, well, essentially what we want you to do is to teach them how to do what it is that you do. And at that point, I had to take a huge step back as an architect and say, to be perfectly honest, I have no idea how I do what I do. As an architect, I go to a room with people in it and I talk and they seem happy, and there isn't really a structure to this. And there are architects and there are courses and there are people who pretend there's a structure to what we do, but there isn't actually. It's all very contextual, very reactive. And this isn't a surprise. This book from 1981 by Donald Shand talks about the reflective practitioner and how over time, through exposure to many, many contexts, we build up a set of instincts by reflecting on past experience. And this book tells us how this is very, very common. And this book has nothing to do with the IT industry. This is for all professionals working in complex environments, that we eventually learn how to survive in those complex environments. And it's not something that is codified or particularly easy to teach. And so, given that, I went away and I started to think about, well, what is it that I do? What is it that other successful architects around me do in order to deliver these seemingly impossible solutions? And what is it that the architects who are struggling, what are they not doing? What's the difference? What's happening here? And I landed then on uncertainty. This is a problem of uncertainty. How do we do something? How do we do anything when we don't actually know what's going on? And that led me from various different starting points to the complexity sciences. And the complexity sciences are obviously endlessly fascinating, but they're also incredibly large and a lot of different opinions and different ideas within complexity itself. And one of the things I've noticed over the past 10 years is that there's a lot of people who'll stand on stage and they'll talk about complexity and they'll talk to software engineers, and people will be entertained and they say, wow, this is really interesting. But at the end of the day, we're always left with the same question. What's the point of complexity science, and how does it change what we do as software engineers and architects? There's a lot of big words and a lot of nice ideas and a lot of concepts that seem familiar, have some kind of resemblance to what it is that we do. But how do we actually put this into practice? And that's been a big gap when we talk about complexity and software. And so to do that, first we need to set up a few definitions to talk more deeply about this. The first thing that I've defined is the concept of a hyperliminal system. So a hyperliminal system is exactly what we talked about in the problem. We have this ordered, structured, mathematical thing, which is software. And it does what we tell it to do. It can be tested, it can be refined, and we're in control of it. And we place it into this unpredictable, uncontrollable mess of people and organizations and all of those things that you're used to talking about on this forum, I'm sure. And as an architect, you have to start off in here, in the ordered system, and you've had your education, you've been to university and you've learned all about these ordered systems, and you've learned about logic, programming languages, and how to test and all of these things, and your algorithms and data structures and all of this ordered mathematical stuff. But then, and this is usually a shock to most newly graduated software engineers, then you've got to step out into the real world and you've got to talk to people, and they're all full of madness and telling you lies and not really sure what's happening and what's going on. And then you've got to bounce back into the software and you've got to bounce around all the time. And so you're constantly in between these two worlds, this world of order and structure and logic and mathematics, and this world that for you is unmapped and wild and chaotic in your experience of it. And so what we have then is an ordered, structured system surrounded and influenced by, these two things are not separated, this boundary is incredibly permeable, influenced by an environment that is impossible to map and control in the same way. And there's completely different skill sets that are required to manage these two things. And this is what makes architecture incredibly difficult. And it also what makes it unique. So if we go back in time a couple of thousand years, we go back to Greece, and there's a guy there called Heraclitus that you're probably all very familiar with at this stage, and he's a philosopher who talks about the world being in a state of constant flux. And you've probably heard the quotation that no man can ever step in the same river twice, because he's not the same man and it's not the same river, and that comes from Heraclitus. And Plato then, who's influenced all of our thinking, essentially, in the Western tradition, talks about something completely different. He talks about a world of objects and ideal forms in something that's called essentialism, the idea that everything in the world is some form of a copy of an ideal form of that. And Western philosophy has centered on this form, on this object, on this thing, on giving a thing an identity, on isolating a thing, describing it, controlling it, understanding it, experimenting with it. That is the way we deal with the world around us. And this closes an awful lot of doors to us. It means that we're focused on identifying the thing, working with the thing. What is the thing? Where is the thing? What's its relation to other things? And that's not actually how the world works. The world works in a completely different way, much closer to what Heraclitus described. And what we tend to do is we tend to reduce these flows of things that are happening in our environments to a single structure, and we try to understand the structure, and we try to control the structure, and we try to control the flows and the madness that's happening around us through that structure. And this leads to the fact that software architects then, what they tend to do, and this is repeated across the entire industry, is that they tend to absorb an accidental philosophy that they're not entirely aware of. So if you ask an architect, what's your underlying philosophy? What do you believe in the world to be? You won't get a particularly sensible answer from them. Whereas if you ask a doctor, what's the philosophy of medicine, they'll at least be able to give you some kind of credible answer, at least around first do no harm or something like that. And that accidental philosophy has a number of pillars. And the first is this Platonic essentialism, this idea that there are objects or forms or ideal forms that we can work with. And you see this in software architecture everywhere. You see it in something called object orientation, where we try to describe our entire architecture as a network of interlinked objects, and these objects have properties. You see it in architectural frameworks like the Open Group architectural framework, which is known as TOGAF. TOGAF talks about things like architectural building blocks and solution building blocks, and this idea that we can break things down and find the essential form of things in order to make them reusable. There's also some elements of structuralism in how we think. We believe that there are structures somewhere hidden in language, and if we investigate these structures in the language, then we'll get control of things. And you see this in many of the schools of thought around requirements engineering, and things like domain-specific languages and domain-driven design, this idea that by just analyzing language, we will get to the truth about what a system or structure might be. There's also a great degree of naive cybernetics, where we sit inside the system, inside our logically controlled system, our software system, and we project that logic and that control out into this environment around the system. And we say, well, an organization or a market or a society is just a mechanical thing that works exactly the same way as a machine, with feedback loops and all of these things. And that naive cybernetics tends to flow into that as well. And there's also something called the causalities of certainty, which is a very naive idea about how things cause other things. And that comes from a British researcher, British complexity researcher called Ralph Stacey, who I'm sure most of you have heard of in this forum. Stacey talks about the causalities of certainty, our belief that there is efficient cause, if A then B, and that there is rational cause, that if a bunch of smart people sit down and engage with a complex system, they'll drive the cause to the goal that they want to drive it to, which is not our experience of reality, but it's what we teach and what we tell people. And the fifth pillar of this is the concept of a model, and architects spend a great deal of their time modeling, and that's the bit we're going to look at because that's where we're weakest. All of these four things turn up in our models. And this approach is something that collectively I've called the component metaphor. And it emerges as a need to very quickly map an organization into a bunch of processes or capabilities, which is what architects do, and then map those processes and capabilities into a bunch of components so that we can start working. And all of these share the same single flaw, and that is this thing called substance philosophy in Western metaphysics and Western philosophy, where we focus on the thing, on the object. And whenever, what we do as architects is representation. We have to represent what's happening, and we have to provide a representation that allows us to make structured decisions about a software system. So we have to represent both the environment that we're working in, the people and the processes and all of the stuff that's happening in a business and a market. And we also have to represent the software. And we have to do that. And very often this is done in a hurry. And when it's done in a hurry, we do it in an unthinking way with this absorbed, accidental philosophy. And we tend to focus on things like components and business processes and patterns, which, a pattern is just another way of thinking, here's an ideal form, and let's use the ideal form, let's focus on that. And this is a well-known problem in philosophy. Nassim Taleb talks about the Platonic fold. Whenever we look at the world in terms of objects, whenever we look at the world in terms of these simple models, we miss things. We necessarily have to hide detail in order to make this work. And those X's are in those folds. Deleuze, who we're going to talk about today, because I heard on the last show that you all love Deleuze and you want to hear more about him. Deleuze calls this blocking, that the representation, this focus on identity, causes us to miss things in the systems that we're working. And according to Wittgenstein, who I use as my anchor to keep me sane because I've engaged with continental philosophy and I need to have some kind of balance, what we're doing is representing nonsense because we don't actually know what's out there. We don't know what's happening. It's all speculation. So we take a step back then to an idea that's going to be fundamental to us to understand the rest of this conversation. And we go back to Kant. And Kant talked about this concept of nomina. And nomina is just a fancy word for a thing. And it's a thing that exists in the world. And we as humans, when we interact with that thing, we can't be entirely sure what it is because we're limited most of the time by our senses. We're limited by what we can see and taste and hear and feel. And so we can't get a real complete picture of what's actually out there, according to Kant. I was talking before, we had things like Geiger counters, and we could extend our own senses to things that aren't perceptible to us. But essentially, we have a phenomenal understanding of this phenomenon. It's always smaller than the thing is. So this green circle represents our understanding of the thing, and the white circle is the thing, which is always a little bit bigger. Now, in this picture, what we have is a phenomena which is close to the nomina. So our picture of the thing, our understanding of the thing is close to the thing itself. And we know this has happened whenever we can predict and control the thing. And whenever we can discover natural laws about the things, when we can do science, when we get repeatable results, when things are predictable, then these two things are very close to each other, and then everything's easy. And we can have things like efficient cause, and we can say if A then B in this kind of scenario. The thing that's much more interesting is when we have a thing in the world and we really don't have a good perception of it. And our phenomenal understanding of this thing is very, very small. And whenever that happens, then we get confused. And when we get, and this can happen for two reasons. One is that we're ignorant. We don't understand the thing. We haven't spent enough time with it, and we need to just spend some time going through what is this thing, how does it work, what experiments can I run on it, what can I learn about this, has anyone done this before? The other side of the coin is that sometimes the thing is just so big and moving so fast that we can't possibly get a grasp on what it is. Both of those situations are what we refer to as complexity. They're two very, very different things, though. Whenever we don't actually know, whenever the gap is a result of our ignorance, we call it complexity, but it's not. It's ignorance, and we will figure it out eventually, or we'll get fired and someone else will figure it out. And so we don't really need to spend that much time on it. Whenever you see software engineers talking about things and saying it's really complex, that's what they're experiencing. They're experiencing, I haven't spent enough time with this thing to understand how it actually works. What's interesting to us is whenever this gap is a result of the size and the number of pieces and the number of interacting pieces and the way they interact of the system, that's when it's interesting. And complexity science then is all about this phenomenal gap. Phenomenal gap's a term I just made up to describe this thing. And so complexity science is all about what is this phenomenal gap? What's in there? How do we solve this problem? How do we stop this situation from occurring where we have absolutely no idea what's going on all the time? And so you have things like systems thinking and complex adaptive systems. And once again, unfortunately, they are very much in the Western tradition. They're focused on the thing. And so both all schools of systems thinking and complex adaptive systems, they focus on the thing, and their thing is a system. And just because it's a bunch of things doesn't mean it's not a thing. And so you end up trying to solve things in exactly the same way. What is the thing? What are the properties of the thing? How do we control the thing? How do we generalize the thing? How do we deal with this thing? What's the ideal form of a complex system? And so whenever we talk about, unintended consequences and nonlinearity and emergence and blah, 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 that's all just trying to focus on this as a thing. We're just engaging in the same way of thinking that we've always engaged in terms of our Western thinking, and there's nothing wrong with that because it's been very successful. It's just that in this case, with when there's a phenomenal gap, we haven't really been that successful, and in software architecture, we definitely haven't been that successful. So what we're trying to do then is to resolve complexity as a property of a thing, and there tends to be then there are different schools of philosophy, of course. There tends to sometimes be a real mathematical focus, and there's a lot of puzzles, there are a lot of papers published on the intricacies of different types of networks, and I've spent some time there, and I haven't really found anything concrete that I can use in my real work. The complexity sciences are wildly interesting, obviously, and all of you think that too, or you wouldn't be here. And they seem really relevant to what we're doing, because if you're working in the phenomenal gap, then these things are relevant. I would say, if we're critical of our own tradition in complexity science, that there's way too much speculation and there's way too few scientific results. There's way too few things where we can point out and say, look, now we do this works all the time. And complexity science is generally observed by software engineers as being esoteric and really far removed from real world engineering. It's not seen as relevant. And like I said, we're still obsessed with substance, and so a complex system is an essential substance, an essential form, and we give it these properties, and we're essentially reframing substance metaphysics in complexity language. And how do we get away from this? And I think one of the things that really was interesting to me was the work of Paul Cilliers. I'm guessing a lot of you are familiar with Paul Cilliers' work, where he has talked about the similarities between complexity and postmodernism, and he talked a lot about Derrida. And from that book, from reading Cilliers, I started to realize that complexity is actually it's not this new thing that turned up in the 1940s when Norbert Wiener was trying to shoot down airplanes. It's a philosophical problem that's 2,500-3,000 years old. And one of the things we have to be careful of in the complexity sciences is that we actually stick to science. And this article comes from an article by a guy called Stephen Phelan, who talks about what is complexity science really, and he talks about the dangers of slipping into pseudoscience by using resemblance thinking. And so this is something that I've carried with me in my work to make sure that we keep this empirical, that we can actually prove that what we're doing is going to make a difference. And that brings us to residuality theory. So what I did was to read and learn about systems thinking and all of these different schools of thought and complex adaptive systems. And so I'm a mathematician, so I'm able to dive into all those nasty parts of complexity that most of us like to just sweep under the rug. And at the end of the day, what I find was that this is completely overwhelming. There's a lot of metaphor in here, but it doesn't actually tell us what to do as software engineers. And so what I did was something very close to the method of Cartesian doubting, by saying, well, what can we say? What is actually true? What can we say about these systems that isn't speculative, that isn't just a resemblance? And what I came up with was residuality, and it goes like this. We have a thing. And this applies to anything, but it's most interesting to those things that have a phenomenal gap. We have a thing, and that thing is made of stuff. And the stuff is connected to other stuff. That's definitely true. And this thing, something is going to happen, either external to the thing or internal to the thing, because all this stuff is moving and interacting and changing all the time. Something is going to happen. And when that something happens, it's going to change the structure, the organization, the interaction of the thing. And that thing then we call the residue, the thing that's left over. And then another thing is going to happen, because stuff never stops happening. And the future of the system is going to be a function of the residue. And if we boil everything down, this is all we can say. This is all we can say to be true. And as software engineers, as architects, we cannot predict what this thing is going to be. And we cannot predict what this thing is going to be. And we can't really control it either. The only thing we can do as software architects, because we're building structure, is we can control the residue. We can control how the thing falls apart. And that's what we can do. And this is a complete change of perspective in terms of architecture. So we're no longer building things and creating things. We are controlling the order and the way in which a thing falls apart, which is a completely different perspective. And this became the sort of ground, and I'll show you where this fits in a later slide. This is the grounds for what we shall do as software architects. Now, the problem here is that this is actually a philosophical position. I didn't realize that that's what I was doing. I didn't want to do that, but that's what I did. And so this is essentially, residuality is a process philosophy. And a process philosophy is different than a substance philosophy. A process philosophy is what Heraclitus was talking about. And a process philosophy says that the world isn't made up of things that we interact with, but the world is made up of processes, of flows, of constant dynamic change, of constant processes interacting with each other, rather than substances. And that's a completely different way of looking at things. But it's also something that hasn't had a great deal of practical use in the world. In 2021, I wrote a paper on the philosophy of residuality theory, where I came out really hard against these Platonic approaches and said, look, we can't focus on substance, we can't allow the component metaphor to be the thing that defines architecture. And I hinted that post-structuralism might be relevant. And that's a horrific statement to people who come from a mathematical background. And this was the first kind of step away from all of that. And one of the things that was interesting was this idea of postmodernism, and Paul Cilliers is obviously the bridge to postmodernism for most of us who are interested in complexity from the start. And postmodernism is about a rejection of structure, and a rejection of the structures that are there, or questioning of them in any case, a rejection of logocentrism, a rejection of the idea that everything can be defined and controlled. And it was very good at pointing out the problems with the scientific worldview, that the scientific worldview maybe doesn't extend to the social sphere. And it was accused of being fashionable nonsense. And if you read a lot of this stuff, it really is nonsense. And it's intriguing, though, because the component metaphor is a set of structures that actually actively prevent architects from engaging with the world around them. And postmodernism is something that allows us to break down structures and ideas, and that's why it's interesting to us. So I started off with Derrida because of Cilliers, I guess, and Derrida's idea of deconstruction, of breaking down structure and finding the fault lines in ideas. And that brought me to Deleuze, who's got a much more positive take on these things than Derrida. Deleuze is a process philosopher, just like residuality, and there's a whole bunch of stuff that he talks about that's very, very similar to what I'm going to talk about. And the Deleuzian dialectic, the way that he interrogates things, is very close to what we're going to look at. The problem is that his metaphysics is convoluted, it's contrarian, and it's wildly open to interpretation. And when someone like Alicia Guerrero says, I don't understand this, then there's a problem with it. Right? Deleuze is happy to just wander and wander and wander, never to arrive anywhere. But we have deadlines. We have to get something done. Architecture must be pragmatic. One of the most fundamental ideas to Deleuze's philosophy, and one of the ones that's most interesting to us, is this idea of difference and repetition. And Deleuze believes that a thing is not identified by its form or by its properties, but a thing is identified by its differences over time. So the differences that pop up in a thing are what define it. And through repetition, through constantly reliving the same cycles, we get to see the differences. And a good metaphor for this is going for a walk. If you go for a walk, that walk will be new to you. You go for the walk, you learn the way, you learn the roads, where the footpaths are, where the trees are, all of these things. You go for a walk the next day, it's going to be mostly the same, except maybe you'll learn that this house has a dog, or there's a moose in that field. It's a very common thing when I go for a walk where I live. And every day the walk is slightly different, and as you repeat it. And as you take the walk, as you go for the walk, you build up a better understanding of what is this thing, this walk, this path that I traverse every day. And it's not you don't sit down and define the walk. You don't use your Apple Maps to say this is the walk for you. The identity of the walk is all of these differences, all of these things that are different every single day. What it's like in summer, what it's like in winter, what it's like in the spring, what it's like when people are out in their gardens, what it's like when people are inside, these things. So the differences define the identity of the walk. And if back to our idea of the phenomenal gap, if this white circle here is the thing, and this green circle is our understanding, Deleuze uses an idea which he takes from the philosopher Henry Bergson of the virtual. And the virtual is something that's bigger than the real thing, and it's full of potentialities, potential futures. Essentially, difference emerges from these potentialities, and this little diagram here then is a completely different thing than just talking about the thing or the object. And Deleuze and Bergson, who he's inspired by, talk about how humans live in the world by using this virtual, the possibilities. We're constantly actually looking at a thing and we're thinking forward in terms of process. What's going to happen here? What can happen here? And that's anticipation. And so accessing the virtual is something that's absolutely vital to us if we're going to live in a world where we deliver software into systems that we don't quite understand. The problem is, how do we move this beyond mere anticipation, beyond dependency on the past? There's a good article about that, which I'm linking to here. So the paradox that we're in is that the focus on substance, which is a natural part of what we do and how we think about the world, causes us to miss a lot of things. It causes us to miss a whole lot of X's, and that causes our architectures to have poor quality. But we can't move away from that into one of these pure process philosophies because they're incredibly abstract, incredibly difficult, and they don't actually tell us how to get a result or how to do anything. We need to have a representation at the end of the day. We need to have a structure that we can, develop code against and structure our system. And so the world of process philosophy and substance philosophy must be united in some way. We have to pay heed to the fact that these are processes, and we have to produce representations, and that's tough. That's a tough thing that we have to do. So the four things then that pop up as a conclusion to this section. Firstly, we have Wittgenstein's change of heart. So Wittgenstein went from saying that the world is just what it is, and if you can make a statement and you can test that statement, and if the statement is either true or false, and everything outside of that is nonsense. And then over the course of a few decades, he softened and said, actually, there's a fuzziness here. It's okay for the photo to be blurry. That's one symptom. Post-structuralism is another thing. Deleuze's embrace of process, complexity science approaches, all of these things are symptoms of the phenomenal gap. They're all symptoms of the same thing. I think it all can be boiled down to one statement from Henry Bergson, that science doesn't yet have a metaphysics. We don't have a way to organize or talk about this phenomenal gap. And the conclusion here is that substance metaphysics is not a good enough foundation for software engineering. And if process philosophy is to help us here, then it has to offer something sharper than what's there at the minute, because it's mostly abstract stuff that's very, very difficult and inaccessible to most people. Quick note on Agile then. So Agile actually diagnosed this completely in the same way that I have. It said that the substance philosophy, the idea that we can plan and control, the idea that there's a thing like a project plan or a requirement, is demonstrably false. It saw this problem, but then it focused on process, and it focused on the development process. It didn't do anything about the static substance representations of code. It didn't do anything about the component metaphor. And because of that, I tend to call Agile a field phenomenological analysis. It's the interpretation of the experience of the developers in terms of process. And they didn't do anything about the major problem. And so the next thing we're going to do is we're going to look at software from the perspective of the complexity sciences. Now we've looked at the complexity sciences from the perspective of software with a little bit of help from process philosophy. So two things from the complexity sciences that we use to help build a bridge to software engineers, to get them to help them understand that we're on your side. We're doing the same thing here. The first is random simulation. And this is a well-known problem. We have a circle inside a square. The square is of side x. How do we determine the area of this circle? And when I ask this question to someone who hasn't studied these kind of things, you'll immediately start talking to yourself, and you'll say pi r squared. Okay, pi r squared will give me the area of the circle. What's r? And that's substance thinking. You're thinking a circle has these properties, follows these natural laws. There are other ways to solve this problem. And the way that we solve it is, given that the square is of side x, is that we just throw a dart at the shape. And the dart hits the circle. And we throw another dart at it, and the dart misses the circle, but it hits the square. And from that, I can deduce that the circle must be 50% of the shape, which is x squared over 2. And that seems ridiculous. But it's easy to show that if you throw lots and lots of darts and they're random, that this actually works. And you can get very, very close approximations of pi by following this method. And so we don't, so we don't always have to know everything about an environment in order to be able to work with it, in order to be able to talk about the environment, in order to be able to get to an actual scientific result. And if you think about what we do as software engineers, we work with requirements engineering, and we have workshops and we do risk management, and we talk to people and all of these things. All of those conversations, all of those documents, all of those facilitations, they're all random simulations of the environment, because we're dealing with a phenomenal gap. We can't actually go out and grab it and test it and work with it. We have to simulate it. And so a random simulation, which is all those pink points in the virtual, is what we actually do. The second thing that's really important, and this is the most important thing in the complexity sciences from my perspective, is the concept of a Kauffman network. And a Kauffman network, which I'm sure many of you have met before, is a random Boolean network. That is, it's a set of, we can consider them as light bulbs. It's a set of nodes that have two possible values, 1 or 0. So we can model this as light bulbs that are either on or off. And every one of these little light bulbs has a little function inside it, and that little function runs every time we flick the switch. And the function makes a random decision: am I on or am I off? And that's why it's called a random Boolean network. And if we look at any random Boolean network, it will have a number of states, a number of possible states that are 2 to the power of n. And that's an incredibly high number when you have a substantial number of nodes. And so Kauffman ran these experiments as computer simulations, not with real light bulbs. And the number of light bulbs in his simulation was 100,000. So 2 to the power of 100,000 is an incredibly large number. There's no way that we could ever grasp that number of possible states in a system. The phenomenal gap in that kind of system is so large that we might as well give up, because we'll never grasp it. However, he noticed something strange happening when he started to add connections between these nodes. And at a certain level of connections, he noted that the number of states fell to roughly 317, roughly the square root of the number of nodes. And so simply by connecting nodes in his network, Kauffman noticed that the number of potential outcomes, the number of potential states that this thing can happen in, falls to a much, much lower number, root n in this case. And 317 is still quite a lot of states. It's still there's still a phenomenal gap here, but it's much, much more manageable, and we can close that gap much, much easier. He called these states attractors, because it seemed like the system actually wanted to be there. The system was attracted to this particular state. It kept returning and returning and returning to the same state. And so this is what an attractor is. And it's important for us, I think, in when we're working with complexity, to use this definition of attractor and not get caught up in the sort of deterministic chaos, strange attractors, and all of that weird math that people pretend to understand. This is a much softer definition of attractor. And this leads to some interesting insights, and I call this an NKP analysis. There's 3 properties of these networks that are really, really interesting. The first is n. N is the number of nodes in the system. And in this case, it's 12. And the second thing that's interesting is k. K is a measure of the number of links in the network. And in this case, we're going to take the max, k max, which is the maximum number of links which for this node, and that is 3. And the other thing that's important is something which we call P, which is bias or probability. And if this node here is going to send a signal either to this node or this node, and it sends a message here 50% of the time and a message here 50% of the time, then we say that this node here has no bias. It's democratic, it spreads its messages. But if we take this node up here and say that it sends a message this way 95% of the time and this way 5% of the time, then that node has bias. And Kauffman noticed that the higher n gets, the more attractors a system will have. The higher k gets, the more attractors the system will have, and the more chaotic the journey between attractors will be. And so as you raise n and raise k, you'll tend to get a system where the phenomenal gap grows, where we don't actually understand what's happening. And he found that you can raise k to a certain level, and then we lose our ability to engage with the system, and we call that chaotic. But we can use p, the bias, to calm things down. So as you raise k, as long as you raise p in the nodes, then you can actually get more control over the system. Now, if we think of n as the number of components and k as the link between them, and P as a set of good practices within software engineering, where we determine the way a component communicates, the number of messages that it can take, and the format and structure of those messages, and who it can communicate with, then that's how we introduce bias into a system. And so what we can actually say about software engineering, and this is a bit of a jaw-dropping moment for most software engineers when they see this slide, is that all software engineering is essentially a two-step algorithm from the perspective of complexity. It's a random simulation of the environment, followed by an NKP analysis of potential structures. Every software project ever has involved this. And every software methodology, when you scrape at their words and the way they describe things, no matter which methodology it is, you will find these two things underneath. Every software engineering project is essentially a two-step algorithm that's already well known to the complexity sciences. And so this is the bridge that we can build between the two things to understand what's actually going on. And so the things that we have to do now is put all of these things together: residuality theory, process philosophy, the virtual, the phenomenal gap, and the random simulations and the NKP analysis. And what we do is we use this concept of process, and we make the random simulation more random and the NKP analysis more explicit. And so what we do is we bring Kauffman in, and we add Kauffman to the concept of residuality. So we bring in the idea of attractors, and we bring in the ideas around NKP analysis, and we add that to residuality. And what that does is it allows us to bring the world of process, which is about the residues, and the world of substance, which Kauffman is describing, together into a single model, so we can work with both at once. And what we do then with Kauffman is we also say that the goal of the systems we're building is not to find everything, is not to discover every possible X that there is, but to build something called criticality. And criticality is something that Kauffman also talks about. And you might be more familiar with this as the edge of chaos, which was written about by almost all management consultants engaging in complexity. And so we have n and we have k, a certain number of n and a certain number of k. And when we have a very low n and a very low k, that's a very low number of components with a very low number of connections between them, then we have a system that's going to be very simple to understand. It's going to have a very small phenomenal gap. It's going to be easy to manage, easy to control in most cases. If, on the other hand, we have a system with a huge n and huge k, then you're going to have a huge number of attractors. It's going to be a very large phenomenal gap. It's going to be difficult to work with. And we're going to experience that in a completely different way. And hyperliminality is kind of putting these two things together. Kaufman then talks about criticality, which is this line, this balance between n and k, where a system is understandable, where the phenomenal gap isn't particularly is still big, but not enormous, not inaccessible, where it's not entirely stable, but almost stable, and it has some ability to change as X's pop up. A system on this line of criticality will be able to cope with the changes as we move towards them. And whenever we talk about residues, we have this journey where something happens and the system changes. And when something happens, a system will either die or it will change in some particular way. It will reconfigure itself. The residue will be different than what was there before. And that residue will define what's going to happen in the next step. And the system will break up again. And the next step and the next step until the system reaches criticality. or it dies along this path. And if you think about Taleb's anti-fragile, where he says an anti-fragile system is a system that gets stronger when it's exposed to stress. Well, that's actually what's happening here, where the system is being exposed to stress, the residues are moving towards criticality. It's not something that's guaranteed to happen because a lot of systems die, but this is how we get the idea that a system becomes stronger when it's exposed to stress. And that's because when you expose a system to stress, it forms residues, and those residues can, in some circumstances, move towards criticality. And criticality is where you want to be if you're building something that's going to live inside a complex system. And so now that we've got this idea of attractor networks, so you can, this larger bubble that we make our software system live in, we can describe it as an attractor network rather than a bubble of a blurb of stuff that we don't understand. And so what we have instead of infinite possibilities is a bunch of attractors. And this is what we need to do. We need to build a software structure that survives the journey between the different attractors that exist in a system. So if we move away from this static representation, the static way of thinking, which is inherent to Western philosophy, and we start to think about this as something that moves, the system will move between these attractors, and the software has to be able to move with them. Otherwise, the architecture is going to crack. It's going to break. And so what we do is we come up with an X. And it can be any X, and we just come up with something in this thing that Deleuze called the virtual. It's a possibility, something that, not a possibility because Deleuze wouldn't like that, a potentiality. The potentiality then pushes us into an attractor. And when it pushes us into that attractor, and it can be anything, and one of the ones I like to start with is to say to architects, start with the X that a competitor will drop their price. How will that influence your architecture? How will that influence how you make decisions about the structure of your code? For a lot of architectures, it's surprised that that's even relevant, but it actually is incredibly relevant. And in this attractor, we'll say that this component will break and this component will break. And our residue is, we're screwed. This thing is broken. It will not work in this new attractor. The reason we use the concept of a stressor of an X is because it's much easier for people to talk about a stressor or something that's going to happen than it is for us to describe an attractor. To sit down and describe all the possible states of all the possible nodes inside a business system is impossible. So we're not going to do that. So there's no point in doing impossible things. So we just talk about stress. Anyway, this residue is destroyed. It's useless. It's no good. The architecture is broken. But we can look at it, as everyone can with hindsight bias, and say, if we'd only done this, it would still work. If we'd had this little green component, this system would still work. And so we take this idea and we park it over here, and we call this residue number 1, and we've changed it. And then we take another X. Something else happens in the environment. Your customers don't like you anymore. Your CEO behaves badly at the Christmas party, something. You're in a new attractor. Does the architecture survive in that new attractor? And you say, well, it would, but if we had this little orange component, it would survive it much better. And you call that residue number 2, and you put it here. And then we get residue number 3, and so on. And what we end up with is we end up with this naive architecture, which we started out with, which was always a static representation. It's always damaged by this Platonic instinct that we have to describe objects and things and properties. And then we have all of these residues. And think of these residues as just constantly going for a walk. Okay, this thing here is the first walk that you've had on a bright summer's day, and you have a certain idea of what the walk is. Every one of these residues is a subsequent walk along the same walk, but there's slight differences. Everything changes as you do the walk. And so your idea of the entire system is not one walk on one summer's day, one attractor, which is what we tend to talk about, but it's actually lots and lots and lots of different walks. And the identity of this system is no longer this static thing, but it's the identity of the system becomes the differences between these residues. And so we've taken a huge step towards what Deleuze is actually talking about. And what we're doing now, even though we're representing this thing, which a lot of process philosophers would get unhappy about, we're actually engaging with process. We're engaging with difference, and we're engaging with repetition. It's a completely different way of doing things. And what happens is then, I'm going to show you some techniques for how we contract, how we pull all of these residues together into a single coherent architecture, because that's the problem with this kind of thinking. The benefit, the reason that we do this, what we notice when we do this, and all of this came out of practice. This theory did not come first. This was an analysis of what am I doing? What am I actually doing in my projects? How do I think? How do I arrange my thoughts? What actually happens with these residual architectures is that when we put them into production, we find that these are the kind of architectures that survive that red X. These are the kind of architectures that survive things that they haven't been designed for. And when something survives something that it hasn't been designed for, that's a sign that we've actually reached this point of criticality. We've reached this edge of chaos, if we have to call it that, where there's where N and K and P are in sufficient balance, where our random simulation has been random enough to expose us to enough attractors to have a system that is capable of surviving things that it hasn't been designed for. The reason for that, the reason that it works, is because there's a mathematical leverage here at play. And so what we tend to find is that one residue will apply. Generally, one residue will survive in more than one attractor. If you're following basic software engineering practices. And each attractor in turn has a whole bunch of potential stressors that will push the system to that particular attractor. There's not just a one-to-one relationship. And all you have to do as an architect is identify one X, one stressor, one thing that's going to hit your system. That X will push the system to this attractor here, which will allow you to identify this residue and take the measures that you need to take for your system to survive that particular X. What you get for free is that your system will now be able to survive all of these X's. And these X's are not predictable, or you could never list them all out. They're not things that you know are there. And so what you get is a system that seems to magically survive things that it wasn't designed for. And that's what these competent architects have been doing for years, but they haven't been able to articulate it because they haven't had access to the complexity sciences, and no one really talks about the problem with representation, the problem with a static view of our universe. There's a problem with doing this kind of thing, though. And there's something called the curse of high dimensionality. Whenever we try to talk about what X is, what's going to happen, what can happen in this system, whenever we try to explore the virtual in order to expose the differences and the attractors and all of this, we tend to focus on this little red circle in the center. We tend to focus on things that we think are highly probable because that's what people do. Our projection of the future is based on our ability to anticipate is based on the past. And so we're really bad at actually randomly simulating these things. And if you put people in a group, then they constrain each other. They're afraid to look stupid. They're afraid to say something daft. And this is something I've historically combated by using as a stressor the fact that giant fire-breathing lizards are going to come to your town and destroy your town. And the question after that is, what's the residue? What's left when these giant fire-breathing lizards attack your city? And the thing that's left is nothing. So you've got to think about, well, how do we deal with this? And you've got to say, well, maybe we've got to have a data center in another town. Maybe we've got to have some employees spread out a little bit so that we can still operate as a company. I mean, obviously it's tragic, this thing with the lizards and all, but we got to keep making money. And this helps students do two things. One, it stops them from being embarrassed. It means that we can be a little bit more random, and we can use this kind of fabrication to explore more attractors in our system. And number two, it shows them that probability doesn't really matter. You have to get rid of this idea of probability when you're dealing with a phenomenal gap. If probability actually worked in the environment that you're working in, if what you're working with followed a Gaussian distribution, then there would be no need for this conversation, because Gaussian distributions are easy. If something follows a Gaussian distribution and we can measure it and it's ergodic, then the phenomenal gap is incredibly small. It's not relevant to us. We give that to a junior architect at bowling. Probability is not something that we should be trying to ascertain, because it's mostly false. And probabilities in risk management tend to express the opinion of those with most power in the room. And so this gets rid of that need to express things in terms of probability and frees up and makes the atmosphere, it makes it more playful. And this is quite a playful thing. There's a lot of humor, a lot of fun in doing this kind of thing. But at the end of the day, this will result in a stronger architecture. And so what I'm going to show you now is an example from the real world. And this is an example which is slightly fictitious. It's a number of projects that I've pushed together in order to anonymize them. But we're going to build a cloud-based system for the charging of electric cars. And it's going to manage the customer relationship when we charge electric cars. And so the naive architecture, which in this case, as all naive architectures was put into production, is that a customer will sign up, they get a little key fob home in the post, and they go with this little key fob and they drive up to the charger and they hold the key fob up and it does a little blip NFC thing, sends a message up to a system in the cloud. The cloud says, yes, this person is one of us. They've paid their subscription, let them charge. Sends a little message back down to the charger and the charger starts charging. And this is the naive architecture. So basically that's your first walk. I've just given you your first walk through this system. And what residuality is going to do now is going to force us to take that walk many, many times. You're not allowed to build anything. You're not allowed to write a book about how best to take this walk once you've done it once. We're going to take this walk many, many times, and we're going to encourage variation through the use of stress. And this is a politically correct version of a stressor analysis. And the politically correct version we take out, I'll talk about lizards and stuff because you don't want to show management that stuff. They don't get it. It doesn't work. So there's three things that are really important here that I want to highlight in this stressor analysis. Firstly, we don't actually draw these massive pictures of residues. Okay, we don't draw the entire architecture every single time. We focus on difference. And that means that the architecture, the difference is here in the mitigations on this side of on this side of the thing. And that means that we're focusing on difference, and we're actually reaching a concrete example of Deleuze's idea of difference being the thing that identifies a thing rather than properties and all of that, which is an achievement in itself. And if we look at these, there's three things here I want to look at. One is stressor number three. Stressor number three is a field login, okay? And this happens a lot. Someone drives up, they hold up their little blippy thing, and it doesn't work. And it doesn't work because these things are incredibly sensitive to heat and cold and being chewed by babies and magnets and all of those things. So for some reason, it doesn't work. What's the residue when that doesn't work? The actual residue for the business is you have an angry customer, you have a half ton of metal parked in front of your charger, your asset, so it can't make money. And that person isn't going to drive away. And the simple reason that they're not going to drive away is that they probably have no electricity in the car. They can't go anywhere. There's no charging station nearby. This is not a good residue. And you want to get out of this situation. So we want to add that little green box. How do we make this better? And it turned out that the change we wanted to make here was to add something called ALPR, Automatic License Plate Recognition. And so we changed the architecture. And what happens is then if someone doesn't have a key fob or the key fob doesn't work, we scan their license plate and we let everyone charge. We don't block anyone from charging, so we avoid that nasty residue, and we'll invoice them later on registration because we have their number plate, and in a huge number of jurisdictions it's possible to get someone's home address and send them a bill. And that changes the entire structure of the architecture. And so we take a whole bunch of different walks through the system. And the next one that's interesting is number 8, or 8, as they say in proper English. And what happens here is that there's damage to the charger, criminal or accidental damage. People are going to drive into these things. And we solve that problem by having some redundancy, by having sensors, by having security cameras to encourage people not to wreck the place or not to drive off if they hit it, that kind of thing. And the next thing that's interesting is stressor number 12. The stressor number 12 is an actual problem for these systems. People plug their electric car in and they go away. And this is a huge problem, especially near golf courses. People plug it in, they go away for hours and they don't come back. And then your asset is stranded because a fast charge is meant to be 25 to 30 minutes. This is a huge problem. How do we solve it? Well, what we do is we use something that's already there in one of our other residues. This is a recurring pattern that you'll see. And we change our business model slightly. So we invoice per minute, and we invoice on a sliding scale. The first 25 minutes are part of your subscription. After that, it starts to cost money. And the next 25 minutes, it costs even more money per minute. And eventually what happens is you get this astronomical bill if you park your car there for 8 hours and block it for everyone else. And then from the company's perspective, from a financial perspective, that's good. We're going to make more money if you do this. So we've gotten stronger because of this particular form of stress. And most users will, not want to pay those fees. And all so far so good. You can say that there's nothing going on here that wouldn't go on in a normal round of business development. And then we start to see some really interesting stuff going on here. And stressor number 14 is the one that's interesting. Stressor number 14 is something called icing. And ICE stands for internal combustion engine. And icing is a thing that started to happen in the United States, where people would park their pickup trucks, their fossil fuel driven pickup trucks, their ICE trucks in front of the electric chargers. Why were they doing that? Because they assumed that ownership of an electric car was a political statement. If you buy an electric car, you care about the environment. If you care about the environment, you vote for a particular political party. It's not the same political party as me. I don't like you. I'm going to make your day worse by parking there. And this is one of those X's that pops up, and it's a result of social pressures. It's a result of social media. It's a result of a whole bunch of things that there's no way on earth you're ever going to predict this kind of thing is going to happen. And what happens is the combined effect of the residues for stressor number 3, stressor number 8, and stressor number 12 combine to make sure that this doesn't happen to this particular company. Because if someone parks in front of the thing, we have your license plate and we have you on security cameras, so we know you, because there's going to be there's going to be a police complaint about this, because you're engaging in sabotage, and also you're going to pay per minute. So if you stay there for longer than 25 minutes, it's going to hurt. We still get paid. You're going to have to pay a lot, and you're going to be reported to the police. And so this becomes a non-problem, and this is what we see over and over and over again when you take this residual difference and repetition approach to architecture, is that the architecture starts to survive things that nobody could possibly have known about. And that's the benefit of this method. And when you run your stressor analysis, when you run through it like this, you'll find that sooner or later it starts to loop. It starts to get really, really difficult to stress the system. You can't come up with anything, because every time you come up with something like icing, you'll notice that a combination of the components are already there and already solving it for you. And what that means is that in Kauffman terms, you've reached criticality. You've got an architecture that's critical to the environment that it lives in. And if you thought this was an American problem, it's turned up in Europe. This is from a German newspaper, Süddeutsche Zeitung, and they've connected the ownership of an electrical vehicle to vegetarianism, and they started stuffing mincemeat in the chargers. And if you work with requirements engineering or risk management, there is no risk management document, there's no requirement anywhere that says someone's going to stuff mincemeat in the chargers. This is the kind of thing in these kind of environments that you simply can't pick up. This is part of the phenomenal gap. And so the final thing that we do is called contagion analysis. And contagion analysis is basically this NKP analysis. And we use a bunch of different tools to decide how do we contract all these residues into one. And one of the things that happens in this kind of system is that you come up with this. Let's say this is your architecture. This is a component structure. It's ordered, structured, and you followed best practices, and you can see here that they've split the components up because they think that certain things are going to happen, or going to change at different rates. What happens is that a stressor will pop up, an X will pop up, and it will hit component C. But at the same time that it hits component C, it will also hit component G. Now, this is the kind of thing that it's very difficult for us to think about, because we've separated these things. We're thinking in terms of objects and properties. They're not connected for us anymore. In network science, when you have this kind of relationship between the stressor in C and the stressor in G, this implies that there's a relationship between C and G. They're coupled in software terms. And it turns out that when you run this kind of stressor analysis over a system, what you'll find is a spider's web of these invisible coupling links between components. And if those components have no direct connection to each other, then they're not functionally coupled. They're actually non-functionally coupled. And it turns out that this stressor analysis is an exceptionally good way of discovering non-functional requirements. And this method is much, much more efficient compared to going to some poor stakeholder who doesn't have a clue what the word means and saying, what are your non-functional requirements? This is a much better way of figuring out what should this system actually be. So with that in mind, we can go into our contagion analysis. And contagion analysis goes back to the concept of that we're working with networks here, and we start to express things as networks, but networks are messy and we don't want to draw them. So we start to use matrices. And the first kind of matrix we use is something called an adjacency matrix. And an adjacency matrix just says who's connected to who. And here you can see a bunch of components, and we put them into this adjacency matrix, which is also known as a design structure matrix. And this is what they do at MIT when they're building airplanes and spaceships, and to figure out what the component structures are there. And here you can see a nice little neat process. And this is an easy system to build. What we look for then is this kind of mirroring. This is an interdependency between two components when you see this mirroring in the dependency matrix. And this is an indication that things aren't going to be good here. What we're actually doing is we're doubling K in our system. What happens when we double K? We have more attractors. We get less stability. And we'll see this. We'll see some systems. You'll see lots and lots of this mirroring. And that's an indication that the phenomenal gap is huge here. The business doesn't actually know what they're doing yet. They're not describing things in the right way. Or your software engineers are trying to solve too many problems in one place. And they're trying to boil things down to an essential form. So this is a result of Platonic architecture. Or you can have this kind of insanely high K. And sometimes this can actually be a valid business model where things have to be loose and have to be flexible. And I have some examples of that, but I don't have time to go through those tonight. And here, the phenomenal gap is enormous, but it requires a great deal of flexibility. But the real magic happens whenever we start to look at something called an incidence matrix, and we break our systems down into stress and flow and component function. And what we do is we take all our stressors, and this is obviously a limited version to let you see the example, and we take all our potential components that we're looking at the minute, and these can be flows, or they can be components, or they can be functions. And if the stressor hits the component, we give it a 1, and if it doesn't hit it, we give it a 0. And then we add them all up. All the rows and columns, and this gives us an absolute wealth of information about the software structure. And this is a network. This represents all these residues connected to each other. Here we can see that this particular stressor has a very high number of impacts. That's nasty. That's something that we need to deal with, or it's going to hurt. What we also see is that if two functions, two components, both have a 1, and there's no functional coupling in our adjacency matrix, that means we've discovered a non-functional requirement. And that's a good thing. Another thing that happens here is that we can look at those components that are exceptionally susceptible to stress, and we can ask, why is this? Have we done something wrong? Has this component got too much going on? Why is it exposed to so much of the environment? And if it has to be, then how do we protect it? And then we can bring in questions about redundancy and diversity in our solution. Other things we can do is that we can discover hidden relationships. And so here I've brought in this function, or this component called unlock car. Now, unlock car was considered to be separate from the solution because unlock car lives in the charger, not in the cloud. And if you look at this stressor, server failure during charge, then you can see that it will hit the stop charge command and it will hit unlock car. And this reveals a coupling between stop charging and unlock car. And that's that's a hyperliminal coupling. There's a relationship between these things that we haven't seen. When that server fails, people who are charging their cars, who are locked in, are not going to be able to leave until the server comes back up, because they're not going to get that command. And this required a rebuilding of the architecture. So just by expanding things a little bit in the virtual, we can find these connections that we wouldn't find otherwise. Another thing that comes out of this is that if we take those functions or components that have the exact same response to stress, and you can see that these two, this one and this one, have the exact same response to stress. That means that these components deserve to exist in the same place. They can live the same life, they will die the same death, they will change pretty much in the same way. And so we can actually deduce the entire structure of an architecture from this matrix, rather than asking an architect, how did you come up with this structure? How did you come up with these things? And they say, I don't know, I followed this blog that I read last week. Or if they're honest, they'll say, I run entirely on gut feeling, a la Donald Schoen's reflective practice. And I have no idea, as I was forced to say 8 or 9 years ago, I have no idea how I do what I do. Well, now we know how we do what we do. And this matrix is the result of this. The final thing then is that we can empirically prove that we've done something useful. And what we do is we take the naive architecture, which is our first walk, and we take a bunch of stressors and we produce the residual architecture, which is this thing that we've just built with the matrices. And what we do is we keep half of our stressors in a drawer somewhere. We don't use them. So what we're doing is we're mimicking the kind of training set, testing set methodologies that you see in ML projects. And we're going to use the set of red stressors to prove that we've actually done something useful. And so what we do is we run the red stressors over each architecture. And we run them over the naive architecture. And every time it survives one of the red stressors, we give it a point. And at the end, we add up all those points and we call that X. And then we run them all over the residual architecture. And if it survives, we give it a point. If it doesn't survive, we get 0 points. And we add those up and we call that Y. And for those situations where neither architecture survives, we look at them and say, which one's in the best position to move? Which one is the least damaging? Which one costs the least to respond to? And we give 1 point to that system. And then we can do this little calculation, Y minus X, which is the difference between these two things, divided by S, which is the total number of red stressors. It gives us something called the residual index. And the residual index then is a number between -1 and 1. And if the residual index is greater than 0, then we've actually done useful work. If the residual index is greater than 0, if you go back to the criticality thing that I showed you in Kaufman with N and K, it means that we have taken a step on that. We've moved in this direction towards criticality. So we can actually prove as architects that we've done something useful, and we can run through this many, many times, and we can look at the residual index every time and say, are we moving forward or are we moving backwards? And so my PhD thesis is going to be based on an experiment where this is run over many projects and show that the residual index is consistently enough above 0 to show that this empirically works across different projects and different contexts. And so we've come all the way from postmodernism to actual empirical scientific proof, which is something that doesn't tend to happen very often. And so I guess a lot of you maybe aren't software engineers, maybe aren't architects, and so you're asking yourself, how does this apply to my particular domain? How does this apply to other things? Well, residuality is, as we've talked about, it's essentially a metaphysical position. It's a process philosophy with focus on residue rather than Deleuze's focus on difference or events. And on top of residue, I've built something called hyperliminality, which is this concept of an ordered system that is exposed to a disordered system. And on top of that, I've used Kaufman's NK model, and on top of that, stressor analysis, on top of that, contagion analysis. And when we put all of these things together, we actually have a model that allows us to engage in empiricism. It allows us to say that this thing is either working or not working. It allows us to be scientific about the thing. if we were to take one of these away, for example, if you take away hyperliminality, then you lose this imbalance between the number of attractors in the business system and the number of attractors in the software system, and it's maybe not quite as efficient. So you need to be very, very careful if you're going to apply these ideas to another kind of complex system. You'll need to build a stack exactly like this, where you justify each step. And in order to have something that remains scientific. So one of the things I would hate to see is that people take the idea of residuality and use it as a metaphor and apply it to anything, which is what happens to a lot of things in complexity science. They, well, this looks like a residue, let's use residuality. And then I don't want to start seeing all these weird matrices everywhere. And here's a matrix of orange seals in Florida or something. That's not going to make sense. You need to build these structures up. Every time you engage with this, it'll still be a scientific project. And so what this is then is a new theory of software engineering, essentially. It's based on the complexity sciences. It's very much focused on solving problems within software engineering. It is probably applicable elsewhere. It's providing concrete tools. These things are easy to use. In a couple of days, developers and architects can be up and running. And more importantly, they can have a structured language that they can communicate with each other with. It's properly researched. So one of the things I decided to do a couple of years ago was, instead of just publishing one of those books with a pretty animal on the cover and going on a speaking tour, I decided to put this through the ringer, to actually go and do a PhD and force these ideas to be, beat up in an academic way. And it's a very, very painful experience, but in the long run, it's working quite well. And also that these ideas are compatible with all other methodologies. So people sometimes get upset because I'm rejecting, and when I talk about the Platonic approach to component metaphor, I'm rejecting what we traditionally called enterprise architecture. I'm saying things about agile that aren't overly positive here, and that causes a lot of people to get very upset. But you don't have to stop doing anything that you're doing. Using these ideas will improve the situation. And yeah, there's a broad body of work on this now, both academic articles and some commercial articles, and even an article in a philosophy journal, much to the horror of my mathematics professor, who I think may be on the call. As I said, most of what we talked about tonight is, especially in the second part, is in this paper, and there's another paper coming that's going to talk about the similarities with Deleuze and process philosophy and things like that. These are my contact details, if you want to find out more. And with that, I'll turn it over to Yoko and Barbara for any questions or thoughts that you have, or if our Zoom bombers have anything intelligent to say.
That was awesome, Barry. Thank you so much. I have so many things to think about and so many thoughts, but we do have questions coming up. So Chris Matz, you were the first one to raise your hand, so go for it, please. And Barry, if you could stop sharing your screen in about 2 minutes so I can see the hands more readily, that would be great.
Okay, yeah.
Okay, I'll lower my hand. So Barry, absolutely loved that. I really loved it. I think there's a lot of things I'd like to discuss with you about it, and so I'm going to just kind of focus on one little thing, which is, so I came at this problem that you've kind of come with the similar solution to the one I've come, which is I look at it as I was asking the question of the why do we have an architect, and I came back with I think a similar answer to yours, which is that they are responsible for the future risk of the system, the ability of the system to respond in the future. And I actually came at it from real options and postmodernism. Actually, it was historiography. And as a result, I came up with a lot of conclusions very similar to yours, which is about the, probability is a complete red herring and it should be destroyed anywhere in risk management. But the other one I'd like to, and it's possibly a conversation we should have future as well, is what we got from real options was the temporality aspects of it, so that when we look at the system from a business perspective rather than from a technical perspective, we start considering the temporality, which means that we don't necessarily need to build all of those residuality, I think you call them. Yeah, because we look at it and we say, right, okay, if given this stressor, this is the possibility of what would happen. And the question we asked was not, how long would it take us to fix that? The question we always asked, because we'd never know the answer to that. The question we asked was, how long can we survive as a system with that in place? Yeah. So we kind of, so there's a, as I say, I've got a very similar form I teach people, almost identical, apart from the fact that I bring the temporality in that says, and how long can you live with that? And how are you going to actually detect the emergence of that particular thing? So I'd like to hear your thoughts, really. So I've kind of just said, Roy, but I'd like to hear your thoughts on, is the temporality coming into your work? Because it felt like you were describing the technical system rather than the socio-technical system.
Yeah, so temporality is absolutely a part of it, because this is a process philosophy, and temporality is a massive, massive part and a venue for endless discussion in process philosophy. So what I'm saying is that, so we focus on individual residues, which are technical things, but when you put the residues all together and stack them up, because they're related to each other. And so what I'm saying is a system isn't made up of software components anymore. It's made up of residues. And those residues are temporal. So you're never in more than one residue at the same time. You're constantly moving and shifting. And so what you actually have when you put all the residues together is a topological form, which extends through time, and you're moving through that network. And so one of the things I've tried to do is to describe that in networks, but I've given up because it's not actually possible to map it in the same way that network scientists would be able to do with Facebook friends. So temporality is absolutely a massive part of that, and that's the huge advantage of this. So if you look at a residual architecture on the many, many walks, it's forcing an architect out of that instinct to focus on the one frozen moment in time that they usually architect for with a two-dimensional diagram, and it's forcing them into temporality. That's actually not a discussion that you have very often with architects. They see the benefit of this and they do it, and they don't realize that suddenly I'm working with multi-temporal structures in my work. And so a lot of what I'm doing is, so today I'm talking a lot about Deleuze, but I have a feeling that in the future I'm going to talk a lot more about Bergson. And obviously Deleuze is massively influenced by Bergson, but the roots of many of the ideas are in there, and everything that Bergson talks about is based on durée or duration or time. So it's very much an important thing. Detection, which you mentioned, is you've seen, is one of the columns in the stressor analysis. That's something that's very important to any structure.
Yeah, and just I'm being a bit naughty here, Barbara. What a surprise! But I felt that as you were saying about the agile missing this, the agile architecture is very much around the tests and the socio-technical aspects of it, as opposed to the description of the system. And I think as a result, that's why it actually is able to better handle stresses in the system, because it can more easily and safely and quickly, which is the temporal piece, change the system rather than trying to predict the stresses in advance that are going to materialize and affect the system.
Yeah. So at the end of the day, some degree of agility will always be necessary in any structure, any business structure. But the risk is that if you build an agile structure, agile processes, and then you're married to a static representation of an architecture, that architecture, and one of the things I haven't had time to talk about tonight is residual causality. So that when we make structural decisions in our architecture without thinking about temporality, without thinking about stress, it actually lashes back into the environment. And so an architecture can kill an agility that you've spent time building up.
All right, thank you. Really great talk. Thank you.
Yeah, thanks. You're on mute there, Barbara.
Yeah. Thanks, Chris. Peter, you have your hand up, so you're up.
Yeah, thanks, Barry. I'm really curious though. Now you're going through this painful PhD. Will you still put a beautiful animal on the cover of your book? That's my first question. And my other question is like, isn't still the challenge to define the parts that makes up the architecture so that we can have a residue and not start over from scratch for every iteration? How do we define the granularity of the parts in the architecture so that we can have a residue?
Yeah, so I'll take the second question first because the other one's more fun. So we start off with a naive architecture. And when you have a naive architecture, what you're getting is the architect's gut instinct. It's their first round on the walk. And they tend to bring to bear their past onto the system. So if you ask an architect who's used to working with one particular platform in one particular context, then you're going to get the same patterns and the same components and the same choices that they would ordinarily produce, and that's the starting point. And every residue after that is not redefining the entire thing. It's about the residue is about expressing the difference between that naive architecture and the residue. And eventually, as you build up lots and lots of residues, the differences become more defining than the original structure. And you don't have to redefine everything all the time, but in some residues, you're going to find that you have to talk about more of the system because it has a massive impact, and you have to talk about more components, and the granularity changes depending on the impact that the stressor is going to have. And then the final stage is whenever you have all of your residues and your naive architecture, they're actually all in tension with each other because they can't all exist. And that's when you pull the contraction, and the contraction with the matrices helps you decide which components need to be there, which components need to have boundaries, which components need to live together. And that will allow you to, essentially what we're doing is we're making decisions about granularity in the system. Essentially after a certain number of residues, you as an architect start to think of your architecture not as this static thing that you started out with that we're used to after several decades of thinking about an architecture, but you start to think of this collection of differences. Does that answer your question?
I'm not sure, but it sure was an answer that I had to think about for a while. Okay. And maybe I'll come back to you if I'm not happy.
Yeah, with regards to the pretty animal on the front, I have heard that you're not allowed to choose your own animal, and I would obviously have chosen lizards. A
fire-breathing one.
Yeah, exactly. I'm at the minute I'm talking to a number of people, and when the book comes, I expect it to be through a smaller publisher, because there are smaller publishers who have editors who with software and complexity backgrounds, and that's going to save me months of work if I have someone who can talk to me on both levels. But there's nothing to stop me from putting a lizard on the front, and I might. So if you're any good at drawing, send me your lizards.
Oh, boy.
It's gonna be a first naive lizard, and then we can iterate.
Exactly. Yeah.
Okay. All right. Thanks, Peter. We have two questions from Vicky. One is theoretical, philosophical, and one is practical. Do you have a preference as to which one I give you first?
Give me the philosophical one.
All right.
Always the most fun.
Okay. I'm a bit of a Stafford Beer nerd, and it is interesting to me that almost everything I've seen in residuality theory is very similar and touches on pretty much the same points Beer does, including similar criticisms of contemporary cybernetics, science and management practices, and environment. Hell, his famous Puzzywid principle is very much grounded in that criticism. Yet I saw that his VSM was in your list of Platonic systems. So I wanted to pick your brain or mind about that a bit, if possible.
Yeah. So the VSM is a representation. It says this is an organization, and it says this is not only this is an organization, this applies to every organization. So it's a Platonic form. It's an attempt at essentialism. It's a static object, and I'm absolutely not a fan of it. But you mean I do? Stafford Beard, very 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 smart man, great beard, but I'm not a fan of that way of mapping things. I think that what happened there is that we go too quickly into the Western tradition to try and say, this is the essential form, this is the organization, this is the structure of a team, this is the structure of a process. We're way too quick to go to that kind of thing. And what we do when we do that is what Deleuze calls blocking. We shut things out. We shut out other possibilities. So if you were to go in and immediately start describing an organization in terms of the viable systems model, you're going to miss things that are outside of that model that model isn't able to talk about. And given that we're working with a phenomenal gap, we don't know what's there, so we don't know what we're missing. And I find that kind of approach dangerous, which is why I keep residuality at the bottom layer of this is so thin. It's just a very, very simple set of statements, because it can't be corrupted. And I think that's very, very important. I hope that I've answered that without offending.
Yeah, more or less.
Vicky, you want to unmute yourself and go for
counter arguments, but we're not there to have beers together, so I cannot do that. It's always difficult to criticize, especially when people have such a huge influence. But this tendency towards the Platonic model isn't something that's just a feature of cybernetics. It's a feature of everyone who's been alive since Plato, with some notable exceptions, but they didn't build any systems. And it's not a specific criticism of that. It's just there's a pattern that I see turning up again and again and again. And the second question was, which I think was technical.
Yeah, Vicky, you want to ask that yourself?
Yeah, definitely. So from the example that you give, a lot of the things that are listed there seem like individual class or maybe a function. And one thing that I've encountered when working in reality is that very often you would have the classes, the functions, and so on that all live in, say, a Docker container that is deployed on a Kubernetes cluster, that there's a bunch of Azure pipelines that do the deployments and so on. So when you're doing this analysis, how do you differentiate between the different levels? How do you know which components to include?
Yeah, so I run this. I run it from. This is a lot of detail, so it takes a couple of days to get through this. But I tend to view a system as a set of flows, which is very in keeping with the process way of thinking about things. There's a set of flows, and those flows are broken down into components. And those components are broken down into functions, and then we'll start off by defining flows. Then we move to function. Then we move from function to component. And once we've done that, then you can move to Docker. For me, Docker is hosting, and pipelines is hosting. And you can also run the stressor analysis over your hosts. Once you get to that level, then there's a slide we skipped over on systems engineering, where you have to go in and ask, is the way that I'm hosting these particular components amenable to an architecture that's going to survive long term? And there's a different set of much more technical processes there, which are standard systems engineering things that I do, like Atom and FMIA, that help us to isolate risk in the technical. But at that point, we've moved out of the big bubble and the virtual, and we've moved into the technical and the controllable. And so we already know how to do most of that. And I would say that most of the architects that turn up on my courses, they already know how to do those kind of things. And so I don't spend a great deal of time on it. I do have an introductory course for people who maybe haven't done that kind of stuff yet. I like your down with agile comment, but we're not here to do that tonight. That's definitely something we do over beer.
Okay. Vicky, all good?
Yeah, thanks so much.
Great. Wendy, you had a comment/question in the chat. Would you like to unmute yourself and ask Barry directly?
Yes, and this is coming at not a naive perspective, but I come from a different tradition and not software engineering, but I've discovered by first principles a lot of the things that you've spoken about today. So thank you very much for your very thorough walk through the process. So using matrices and just experimenting a little with that with adjacencies, I think that I've discovered that there's quite a lot of power in just looking for adjacencies either in a systematic way or in a, using narrative, for example, to disclose where some adjacencies are going to turn up with some power in the insights that you can draw from where things are co-located or where they're separate. And so you showed a number of views of different, I guess, patterns that turn up in the system. So do you ever sort of, I know taking a shortcut here is probably not the right phrase, but if you want to get some quick insights about where there's going to be some powerful adjacencies to deal with in the system, because if you just use a 1 to 14, or if you just assign a straightforward order, quite often you can miss things. By reordering things, you can actually get some really quick insights that can give you some big things like mints inside housing mechanisms and other things you would just not have got, real wild cards. You're thinking, wow, I needed to see that process. How do you go about that?
So in terms of technical adjacency, if you just throw things randomly into a matrix, into a spreadsheet, there'll be little ones hanging up around here, or things that you miss, things that you did right in the fringes. There's actually a rather keen set of mathematical tools for doing that. And you can download them for free from MIT. They call these adjacency matrices a design structure matrix, but I find that's a step too far for most software engineers, and everyone gets caught up in the math, and the results get kind of strange. But it looks really pretty whenever they show you this is how we decided on the component structure of the Boeing 747, and they show you all these little these lines in a spreadsheet moving up and down, and all these nice shapes forming. In terms of adjacencies in the wider system, what we do is we use the stressor analysis. And so if someone gives me a matrix, the first thing that we do is we just keep stressing it. We say, is this really the case? Isn't there something else that's linked to this? Are there other possibilities? And just by bringing in the stressor analysis, and so you're never going to go from a matrix where you're talking about these things to mints. But if you go from a matrix from a matrix of, say, you're talking about the infrastructure and chargers and forecourts and all of that, and business models, and you're saying, well, who are our customers? And then you can go from customer to who are our customers, and who are our customers in contrast to who are not our customers. Maybe you can get to something that appropriates that kind of thing. And so the process of stress is meant to say that we're going to take the same walk over and over and over again, and we're going to notice all the differences as we go on that walk, and the identity of this thing is the sum of the differences. And that is that is something that will help us pick up as much as what we possibly can. But there's always going to be something like mints that you can't possibly catch, and the hyperliminality and the balance in terms of the size of these systems and the number of attractors allows us to take the walk a much smaller number of times than we need to in order to produce a structure that protects us against things. And what I try to avoid is falling into the trap of saying that I'm able to describe everything and that I'm able to protect against everything. I won't ever be able to describe every single X in a system, and I won't ever be able to protect against every X that is potentially there. All we're doing is moving the system as close to criticality as we possibly can. And so stress and differentiation through stress are the two things that we do. Sometimes people get caught up though on the fact that I've used the word stress, and it might not have been the best word, but it's too late now. So a stressor isn't something that necessarily stresses a system. It's not stress in the sense, oh, I feel bad, or I can't sleep. It's stress in the sense that I thought this about the system inside my little green bubble, and there's all this other stuff that I didn't know about, and everything that's outside the green bubble is potentially stressful to my representation of what's going on. That's what a stressor is.
And I think there's perhaps a creative act around selecting those stresses and the level of that I think is the wild card and the gift of a really good designer.
Yeah, and there's an article, there's a link to an article on the slide on Deleuze and difference in repetition and the virtual. And there's an article about how the ability to create myths, the ability to talk nonsense essentially, is incredibly important in this process. And Deleuze himself talks about the importance of playfulness and mischief and irony in discovering stressors, which I'm a big fan of, because it gives you an excuse to be sarcastic at work and say you're being productive. But there are no guarantees in any of this. And one of the things that's incredibly important that I might not have mentioned is that this process has to be a crowd. It can't be one architect sitting coming up with all these stressors because they don't have the dispositions to describe all of these things. You have to move and you have to bring in different people and different perspectives.
Yeah, and I was just also, just as I have for the moment, the role of narrative in a sort of dialogic approach. So you get this tension between all the designers, which will kick up things in the intersections that wouldn't exist in other places, another time. And
one of the things I'm going to talk about in the article that's coming is how traditional approaches to architecture, even though they're deeply flawed, some architects get them to work. And what those architects are doing is they're taking all these kind of shoddy static representations, things like requirements engineering and risk management and estimates and patterns, and they're pushing them all together in a way that creates conflict between them, and those conflicts are your differences and your stressors. And so they're essentially doing the same thing. And there's a couple of you who've commented here tonight, and I hear this a lot, which is a really good sign. People will say that this is really good what you're saying. I've already been doing this, but I have different words. And that's because most architects who figured out how to do architecture, there is no other way. This is how we do it. This is our reflective practice. And all I'm doing is lifting it up and saying, this is what we do. And I've used some terms from philosophy and some terms from complexity science to say, this is how we arrive at an architecture. And it's been absolutely fantastic. So I had one of the architects of a major component within Azure took one of my workshops, and they said, this is exactly how we think. We don't have these words for us. We don't get taught this kind of thing in computer science, but this is how you have to think if you're building something that's huge and critical and everything's moving all the time. And that's exactly what I set out to do. So it's fantastic to hear that coming back all the time. We're already doing this. And a shared language, even though I've criticized structuralism here tonight, building a language game inside a company is incredibly important. Pieter has his hand up.
Yeah, Pieter, and I think this is going to have to be our last question, but go for it.
All right, I try to be brief. So could you say that a residual architecture is a resilient architecture, using like Dave Snowden's vocabulary?
I would say that that resilience is a feature of residuality. Yeah. So a residual architecture will show signs of resilience, and it will also show signs of that other thing that Dave doesn't like to talk about, anti-fragility.
But resilient rather than robust.
Yes, resilient rather than robust. And resilience is just criticality. When a system is resilient against something that we know about, where there's no phenomenal gap, then it's just well designed. and we're architects, so we already can do that. When we have a phenomenal gap and we don't know what's there, then resilience is the same thing as criticality. It's the ability to move around. It's the ability to meet things that you're unable to meet. And so I would say that if you build a residual architecture, it will be more resilient than any other technique. But resilience is a byproduct of this. The main goal of this is to give architects a solid theoretical foundation for making the decisions that they have to make around structure. And one of the happy accidents of that is that we build resilient architectures. And so being able to survive stress that we haven't designed for, that we don't know about, that's another definition of resilience. But I find that resilience very often is something that we can only talk about in hindsight. Is a system really resilient? Because even a residual architecture can fall over on day one. That's one of the implications of the phenomenal gap. So is that resilient?
I was actually thinking about that when you were talking, is that the resiliency is actually, as much as we might not want to use the word, but an emergent property of the system. If it can live that long, it's resilient. That's why you would only see it after the fact, right?
Yeah. So, and resilience is, for me, resilience is something we only see in hindsight. I would say that a residual architecture has a tendency, and a provable, if you run the empirical test at the end, it's a provable resilience to things that it doesn't know about. But it's also a word that attracts an awful lot of fluff and an awful lot of snake oil.
Right.
And I tend to not use the word resilience. I maybe did when I was younger and naive, but I don't use the word resilience very much, because everything's resilient in the mind.
The word emergent is even worse, so that's why I said that with quotes.
Yeah. So yes, and Michael says a Lindy architecture is what we have. Criticality is a word I think that has a lot of. It's a very powerful concept that describes an awful lot of things. But definitely, if you're seeking resilience, then run these tools on your software architecture. You'll see a result. If that's resilience or not depends on who the person defining resilience is.
Okay. Well, Barry, this was amazing. I'm going to have to watch the recording, and I've thought of at least 4 topics I'd like you to come back and talk about some more, including maybe a little course for me on Deleuze.
I think the cool thing about what I've done here is that I'm using a lot of Deleuze and a lot of his ideas, but I'm not actually using them, because how do you use his ideas? I have turned them into something empirical, and I've been inspired by them, but I'm not like, let's use Deleuze so we can talk for 6 months instead of actually doing something. If I can just quickly answer Daniel's last question, if you have a downward trend in your residuality index, I'm actually trying to get this to happen for my research. I want it to go badly, because when I run these tests, it works all the time. One reason that you can see a downward trend is that you have an architect who's already thinking like this, an architect who's naive architecture is really, really good. And sometimes it can go backwards a bit. And one of the things that can happen, the path to criticality isn't always straight, right? We can go around in a couple of little loops. So a downward trend means go back and do a little bit more. And if it's a consistent downward trend, then we can say that residuality hasn't worked in this project. And if someone has a project like that, I would love to have it in my research, because I would love to be able to say, this is where it stops, this is where it doesn't work, because it feels too positive right now.
And I guess what I was thinking, or the context is shifting, right? The context isn't stable either.
Yeah, can also happen. Yes. Eventually something will have a very, very strong downward trend and die. But that's the fate of all systems.
Well, yes, eventually we all come to that. Well, Barry, this has been awesome. Jocko and I would really like to thank you so much for your time. And we'd like to thank all of you for joining us this week and hanging in there. And we'll see you all again soon. Bye.